Good morning to everyone. I am Dipanshi from BSc Chemistry Honors second year. Today I am discussing the topic thermodynamics. The first law of thermodynamics had certain serious limitations. To overcome these limitations, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law and as a consequence some definition given to the second law are briefly given below. A major limitation of the first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of energies involved, but it provides no information concerning the feasibility of the process, whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold end to a hot end or not. All that it tells is that if this process occurred, the heat energy gained by one end would be exactly equal to that lost by the other end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to high pressure or water can itself run uphill, etc. The second law supplies the answer to above questions by stating that all spontaneous processes like flow of heat from hot end to cold end, diffusion of gas from high pressure to low pressure, or the flow of water down a hill, etc., are thermodynamically irreversible. First definition. The term spontaneous process used in the above definition means a process which can take place without the help of any external agency. All natural processes, some of which are mentioned in the definition above, are spontaneous process. However, it may be mentioned here that the term spontaneous does not give any idea of the rate of the process, whether the process takes place fast or slow. All that it implies is that a process can occur without the help of an external agency. The first law states that when heat is converted into work, the work obtained is equivalent to the heat absorbed. However, it has been seen from the experience that the heat absorbed cannot be completely converted into work without leaving some change in the system or surrounding. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is lost to the surrounding or wasted in overcoming the friction. Hence, the second law is stated as follows: the complete conversion into work is impossible without leaving some effects elsewhere. Besides the above definition, number of other definitions have also been given to the second law of thermodynamics. The two important ones are: it is impossible to construct a machine functioning in cycles which can convert heat completely into equivalent amount of work without producing some changes elsewhere. Without the use of an external agency, heat cannot by itself pass from colder to hotter body. The term functioning in cycles is introduced in the above definition to indicate that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, delta U is 0, Q is equal to W. The work done is exactly equal to the heat absorbed by the system. In other words, in this process, heat is completely converted into work. However, it is important to observe that this conversion is accompanied by an increase in the volume of a gas so that the system has undergone a change. A number of other definitions have also been given to the second law of thermodynamics, which we still come across in succeeding sections of this chapter. The fraction of the heat absorbed by a machine that it can transform into work is called the efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machine is eta is equal to W by Q. The machine used for the conversion of heat into work is called heat engine. In order to bring about this conversion, the engine absorbs heat from a heat reservoir at a higher temperature called the source and converts a part of it into the work and returns the remainder to the heat reservoir at lower temperature called the sink. In order to calculate the efficiency of an heat engine, Sadi Carnot devised a technique called Carnot cycle. A cycle is a process in which a system returns to its original state after a number of successive changes. A process conducted in this manner is called a cyclic process. The engine chosen by Carnot called Carnot engine for the purpose of calculation of efficiency was a hypothetical one and cannot be achieved in actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of cylinder containing 1 mole of an ideal gas as the working substance and fitted with weightless, frictionless pistons so that all the operations in the cycle are carried out reversibly. For this reason, it is also called reversible heat engine. The cylinder is supposed to be insulated on all sides except at the bottom so that heat can flow to or from the system or only through the bottom. Further, it is supposed that there are two heat reservoirs, one at a higher temperature, T2 called the source, and other at lower temperature, T1 called the sink. If some operation is carried out by placing the cylinder in the source or the sink, it can exchange heat with it and hence the temperature remains constant so that the process is isothermal. On the other hand, if during an operation, if the cylinder is placed on an isolating material, that no heat exchange can take place between the system and surroundings. Hence, the process is adiabatic. The Carnot cycle consists of four different operations which can be represented on a pressure volume diagram, sometimes called as indicator diagram. These operations are carried out as isothermal expansion. The cylinder containing 1 mole of an ideal gas occupying the volume V1 is placed in contact with the source. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. The path of the process is represented by the curve AB and the gas is ideal and the work done W1 by 1 mole of the ideal gas is given by minus W1 is equal to RT2 ln V2 by V1. Further, for an ideal gas, the work done is equal to the heat absorbed Q2 so that minus W1 is equal to Q2 is equal to RT2 ln V2 by V1. Hence, W1 has been taken as negative and Q2 positive by the latest SI convention. Adiabatic expansion. The cylinder is now removed from the source and placed in perfectly insulating material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enters or leaves the system, the temperature must fall. The reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of the sink. Suppose the corresponding volume becomes V3. The path is shown minus W2 is equal to CV T1 minus T2 is equal to minus CV T2 minus T1, where CV is the heat capacity of the ideal gas. Isothermal compression. The cylinder is now removed from insulating material and placed in the contact with sink. The gas is compressed isothermally and reversibly till the volume decreases from V3 to V4. The process is represented by the path CD. The work done is taken positive. W3 is equal to RT1 ln V4 by V3. During the operation, an amount of heat Q1 exactly equal to W3 will be returned to the sink T1. Heat has been given out by the system using the appropriate convention of sign Q1 will be negative and will be positive so that minus Q1 is equal to W3 RT1 ln V4 by V3. Adiabatic compression. The cylinder is now removed from the sink and placed against the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state is regained. The temperature of the gas rises from T1 to T2. The work done is positive by the convention and sign will be given by W4 is equal to CV T2 minus T1. As a result of these four operations, the system has returned to its original state so that a reversible process has been completed. The net work done by the system will be given by W is equal to minus W1 minus W2 plus W3 plus W4 RT2 ln V2 by V1 minus CV T2 minus T1 plus RT1 ln V4 by V3 plus CV T2 minus T1 is equal to RT2 ln V2 by V1 plus RT1 ln V4 by V3. Since V1 and V4 lie on the one adiabatic curve and V3 and V2 lie on other, it follows that V4 by V1 gamma minus 1 is equal to T2 by T1. V3 by V2 gamma minus 1 is equal to T2 by T1. Comparing equation 9 and 10, we get V4 by V3 is equal to V1 by V2. Putting this value in equation 8, RT2 ln V2 by V1 plus RT1 ln V1 by T2 is equal to RT2 ln V2 by V1 minus RT1 ln V2 by V1. RT2 minus T1 ln V2 by V1. Dividing equation 12 by 2, we get T2 minus T1 by T2, which gives the efficiency of Carnot cycle or engine. During the operation, an amount of heat Q1 exactly equal to W3 will be returned to the sink. Heat has been given out by the system using appropriate convention. Minus Q1 is equal to W3 is equal to RT1 ln V4 by V3. Adiabatic compression. The cylinder is now removed from the sink and placed against insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state is regained. The temperature of the gas rises from T1 to T2. The work done is positive. W4 is equal to CVT2 minus T1. As a result of 4 operations, the system has returned to its original state so that a reversible has been completed. Net work done is equal to minus W1 plus minus W2 plus W3 plus W4. RT2 ln V2 minus V2 by V1 minus CVT2 minus T1 plus RT1 ln V4 by V3 plus CVT2 minus T1. RT2 ln V2 minus by V1 plus RT1 ln V4 by V3. Since V1 and V4 lie on one adiabatic curve, V3 and V2 lie on another. P4 by V1 gamma minus 1 is equal to T2 by T1. V3 by V2 gamma minus 1 is equal to T2 by T1. Comparing equation 9 and 10, we get V4 by V1 is equal to V3 by V2. Carnot theorem. It is clear that the efficiency of the reversible heat engine depends only upon the temperature and source of the sink and is independent of the nature of working substance. Another important observation to be made from the above derivation is that the work done in the cycle only involved isothermal operation because the work done in adiabatic operation cancel one another. Further, as discussed earlier, the work done in reversible isothermal expansion from A to B is maximum, whereas the work done on the gas during the reversible isothermal compression C to D is minimum. Hence, the total work done by the system, the reversible heat engine or Carnot engine, is maximum for the specified conditions, and therefore the efficiency is maximum. The efficiency of a reversible heat engine depends only upon the temperature of the source and independent of the nature of the working substance. Since the quantity T2 by T1 is always less than unity, a heat engine absorbs a certain amount of heat from the source and converts a part of it into work and returns the rest to the sink. In other words, it is impossible to convert heat completely into work. W is equal to Q2 minus Q1. The net work done by the system is equal to Q2 minus Q1 by Q2 is equal to T2 minus T1 by T2. Efficiency of heat engine will be equal to eta is equal to W by Q2 is equal to Q2 minus Q1 by Q2 is equal to T2 minus T1 by T2. The result derived from a reversible Carnot cycle leads to introduction of a new thermodynamic thermal entropy. Thermodynamical scale of temperature. From our earlier studies, we are familiar that a thermometer is constructed most commonly by taking suitable amount of mercury in a glass bulb at the end of a capillary tube and marking 0 at when it is placed in contact with ice and marking 100 when it is placed in the boiling water. The length between the 2 points is then divided into 100 equal parts called degrees. The scale of temperature thus obtained is called Celsius scale of temperature. However, because different liquids expand to different extent, their coefficient of expansion are different, and also they do not expand uniformly over a given range. Thermometers constructed by using different liquids will show different numerical values of temperature between their fixed points. For example, a body may show a temperature of 28.7 degrees Celsius with a mercury thermometer, but may show 28.8 degrees Celsius with an alcohol thermometer. The problem was solved by a study of property of gas. It was found that an ideal gas or a perfect gas ceases to exist at a temperature of minus 273.15 degrees Celsius. This temperature was called 0 degree absolute. The scale developed on this basis is called perfect gas temperature scale and is found to be independent of the ideal gas. However, based on the efficiency of reversible heat engine, Lord Kelvin was the first to develop a scale of temperature that was independent of the nature of the gas taken in the heat engine. This scale of temperature is called thermodynamic scale of temperature or Kelvin scale of temperature. It is found to be identical with the ideal gas temperature scale. The basis of the development of this scale is briefly described below. Suppose there are two constant temperature heat reservoirs, one acting as a source, another acting as a sink, and a reversible heat engine operates between them. The temperature of each reservoir on the new scale may be taken as proportional to the quantity of heat absorbed from the source, and the heat loss to the sink may be taken as proportional to the quantity of heat absorbed from the source and the heat loss to the sink, both of which can be measured. If the Q2 is the heat transfer from the source and Q1 is the heat transfer in the sink, and then if their temperature on the thermodynamic or Kelvin scale are represented by theta 2 and theta 1 respectively, we shall have Q2 minus Q1 is equal to theta 2 by theta 1. Thus, this ratio of the two temperature has been defined in a manner independent of the nature of thermodynamic substance. Taking the reciprocal of both sides of equation of 1 and subtracting the results from unity, we will get 1 minus q1 by q2 is equal to 1 minus theta 1 by theta 2. q2 minus q1 by q2 is equal to theta 2 minus theta 1 by theta 2. Putting theta 1 is equal to 0, 0 of the new scale, we get q2 minus q1 by q2 is equal to 1. This implies that the 0 on the Kelvin scale is the temperature of the sink for reversible heat engine whose efficiency is unity, which is capable of converting heat completely into work. But from equation page number 86, it may be seen that it is possible only at absolute 0 on the ideal gas scale of temperature, leads to the conclusion that the Kelvin scale and gas scale are identical provided the gas is ideal temperature on the thermodynamic scale are therefore expressed in the terms of degrees Kelvin. From it has been found that if lower fixed temperature is taken as equal to the triple point of water, then the Kelvin scale is exactly equal to Celsius degree. For this reason, the temperature on the above scale on which the melting point of ice is taken 273.16 degrees, it is often referred to as degree Kelvin. It may be concluded that the thermodynamic scale of the temperature as defined on the basis of second thermodynamics is more basic than that based on the ideal gas because in any fluid can be used. However, ideal gas scale is more practical than for laboratory use. Concept of entropy as a state function. For a reversible Carnot cycle working between temperatures T2 and T1, it has been seen that Q2 minus Q1 by Q2 is equal to T2 minus T1 by T2, where Q2 is the heat absorbed isothermally and reversibly at the temperature T2 and Q1 is the heat lost and reversibly at temperature T1. The above equation may be simplified as 1 minus Q1 by Q2 is equal to 1 minus T1 by T2 and Q2 by T2 is equal to Q1 by T1. Thus we conclude that Q by T is equal to constant and the heat absorbed or lost isothermally and reversibly divided by the temperature at which the heat is absorbed or lost is a constant quantity for a particular system. Further, in equation 2, heat is absorbed at the temperature T2 and Q1 is the heat lost. If Q1 were the heat absorbed or temperature, equation 2 V can be rewritten as Q2 by T2 is equal to minus Q1 by T1, or Q2 by T2 plus Q1 by T1 is equal to 0, sigma Q by T is equal to 0. Now consider any reversible cycle ABA. It may be regarded as being made up of a number of Carnot cycles drawn across the diagram as shown in the figure, starting from A and going through all the cycles successively from A to B. It can be shown that all the paths inside the closed curve AB cancel each other, leaving only the zigzag path, which is almost the same as the path AB of the reversible cycle. By making each Carnot cycle smaller and increasing their number, it can be made correspond to closely to ABA. The reversible cycle can therefore be regarded as being made up of an infinite number of Carnot cycles. For each of these cycles, we have sigma Q by T is equal to 0. Hence, for an infinite number of Carnot cycles, sigma is equal to delta Q by T is equal to 0, where delta Q is a very small quantity of the heat absorbed at temperature T during the small isothermal change of the reversible process. Further, the above term may be divided into two parts, one for the path A to B, another for the back path B to A. Thus, sigma delta Q by T is equal to sigma A to B sigma Q by T plus sigma B to A delta Q by T is equal to 0, or we may write Q by T A to B is equal to minus Q by T B to A. This implies that the total value of the quantity Q by T for A to B is equal to the total value of the Q by T for the reverse path B to A. Hence, it may be concluded that Q by T is a state function. Its value depends upon the initial state and the final state and is independent of the path. Obviously, Q by T is the change in the value of a quantity or a function having some definite values at A and B depending upon the values of pressure, volume and temperature. This quantity or function is called entropy and is usually represented by the symbol S. Thus, if S is the value of entropy and at A is equal to and SB is the value at B, we must have Q by T is equal to SB minus SA is equal to delta S, where delta S represent the total change in the entropy in going from initial state A to final state B. Hence, entropy may be defined as a state function. The charge in the value of which from the initial state to final state is equal to the quantity Q by T, the total heat absorbed reversibly and isothermally in going from the initial state to final state, divided by the absolute temperature at which the heat is absorbed. From equation 6, the entropy change may be defined directly as the quantity of heat absorbed isothermally and reversibly divided by absolute temperature at which heat is absorbed. It is important to note that as entropy is a state function, therefore the value of entropy changes during a process should not depend upon the path, whether the heat absorbed reversibly or irreversibly during the process. However, since the derivation of above result is based upon the Carnot cycle in which the heat is absorbed reversibly, therefore the expression 6 for the entropy change is valid only when heat is absorbed reversibly. Thus, it is better to use the symbol Q reversible in place of Q. The expression may therefore be written as delta S is equal to Q reversible by T. Further, as entropy is a state function, a small change in its value can be represented by ds. Hence, we may write ds is equal to Q reversible by T. Units of entropy. From the expression delta S is equal to Q by T, it is obvious that units of entropy will be calories per degree. If heat is expressed in calories, further entropy is an extensive property. It is therefore important to mention the quantity of substance involved. It is usually expressed as 1 mole of the substance. Hence, the entropy units are calories per degree per mole. If heat is measured in joules, the units of entropy will be joules per degree per mole. Entropy change in a reversible process. Suppose a process occurs completely reversible condition. The heat is absorbed by the system reversibly and heat is lost by the surrounding also reversible. If Q reversible is the heat absorbed by the system reversible, then the heat lost by the surroundings will also be Q reversible. If the process takes place isothermally at the absolute temperature, then entropy change of the system will given by delta S system is equal to Q reversible by T. The entropy change of surrounding will be given by delta S surrounding is equal to minus Q reversible by T. Hence, the total entropy for the combined system and surrounding will be delta S system plus S surrounding is equal to Q reversible by T minus Q reversible by T is equal to 0. In a reversible process, the net entropy change for the combined state and the surrounding is 0. Hence, there is no net change in the entropy. Entropy change in an irreversible process. If any part of the process is reversible, the process as a whole is irreversible. Suppose the total heat lost by the surrounding is Q irreversible. The heat will be absorbed by the system, but the entropy changes of the system does not depend upon the heat actually absorbed, but it depends upon the heat absorbed reversibly or the quantity Q reversible. Thus, the heat is absorbed isothermally by the system at absolute temperature. The entropy changes of system will be delta system is equal to Q reversible by T. Further, suppose the loss of heat by the surroundings takes place infinitely slow and isothermally at temperature T, then the entropy change of the surrounding will be given by delta surrounding is equal to minus Q irreversible by T. Total entropy change for the combined system and surrounding will therefore be delta system delta S surrounding is equal to Q reversible by T minus Q irreversible by T. Now we know that the work done in reversible process is maximum process. Further, as the internal energy is a state function, the value of delta U is same whether the process is carried out reversibly or irreversibly. Delta U is equal to Q reversible minus W reversible is equal to Q irreversible minus W irreversible. Q reversible greater than Q irreversible, Q reversible by T greater than Q irreversible by T, Q reversible by T minus Q irreversible by T. Delta S system plus delta S surrounding is greater than 0. Thus, it may be concluded that in an irreversible process, the entropy change for the combined system and surrounding is greater than 0. An irreversible process is accompanied by a net increase of entropy. All spontaneous processes are accompanied by a net increase of entropy. Delta S system plus delta S surrounding is greater than 0. The exact calculation of total entropy change during an irreversible process when heat flows from body be at higher temperature to a body at lower temperature than when brought in contact, it may be carried out as follows. Entropy change of body is equal to minus Q reversible by T2. Entropy change of body A is equal to plus Q reversible by T1. Delta S total is equal to minus Q reversible by T2 plus Q reversible by T1. Q reversible 1 by T1 minus 1 by T2. From small changes, the above equation may be written as ds system is greater than dq by T, Clausius inequality. The entropy change for ideal gas will change in PV and T. Consider 1 mole of ideal gas enclosed in a cylinder fitted with a frictionless piston. If an infinitesimally small amount of heat is applied to the system reversibly and isothermally at temperature T, then the entropy change accompanying the process will be given as ds is equal to SQ reversible by T. According to the first law of thermodynamics, delta Q is equal to delta U minus delta W. If the process is carried out reversibly, we may be written as delta S Q reversible is equal to du minus dw. Further, the work is restricted to the work of expansion as is usually, then minus delta W is equal to P dV, where dV is the small increase in the volume and P is the pressure of the system. Putting the value of delta W from equation 4 and 3 we get delta Q reversible is equal to du plus p dv. ds is equal to du plus p dv by t. tds is equal to du plus p dv. Now for 1 mole of an ideal gas we know that Cv is equal to du by dt, d is equal to Cv dt, where Cv is the molar heat capacity at constant volume, Pv is equal to RT, P is equal to RT by V, where V is the volume of the system at temperature T and pressure, and R is the gas constant. Tds is equal to Cv dt plus RT by V dv. ds is equal to Cv dt by d plus RT dv by V. Tds is equal to Cv dt plus RT by V dv. Now ds is equal to Cv dt by d plus R dv by V. ds is equal to Cv dt by t plus R dv by V. Assuming Cv remains constant in the temperature range from T1 to T2, equation 10 may be written as delta S is equal to Cv ln T2 by T1 plus R ln V2 by V1. Dividing equation 13 by 12, P1 V1 is equal to RT1, P2 V2 is equal to RT2. P2 V2 by P1 V1 is equal to T2 by T1, V2 by V1 is equal to T2 P1 by T1 P2. From equation 11 we get delta S is equal to Cv ln T2 by T1 plus R ln T2 P1 by T1 P2. Cp minus Cv is equal to R, or Cv is equal to Cp minus R. So delta S is equal to Cp minus R ln T2 by T1 plus R ln T2 P1 by T1 P2. Cp ln T2 by T1 minus R ln T2 by T1 plus R ln T2 by T1 plus R ln P1 by P2. Delta S is equal to Cp ln T2 by T1 plus R ln P1 by P2.